Welcome to the Earth Observing Laboratories seminar series. My name is Jørgen Jensen. It is my pleasure to introduce our speaker today, EOL's Dr. Jothiram Vivekanandan, or for short, Vivek. Vivek has a Bachelor's of Science in Electronics and Communications Engineering from Madurai Kamarai University in India, a Master's in Microwave and Radar Engineering from the Indian Institute of Technology, and a PhD in Electrical Engineering from CSU. After completing his degree, Vivek had both a postdoc and a research associate position at CSU. In 1991, he joined EOL as a scientist 1, and in 2005, he became a senior scientist. Since joining us, he has been involved in multi-wavelength radar analysis, in the design of the hypercloud radar, in radar lidar work, in fuzzy logic classification of cloud and precipitation particles, amongst many other tasks. In the period 2005 to 2010, he was the facility manager for EOL's remote sensing facility, RSF. He has also been a visiting scientist at the Swedish Institute for Space Physics in Kiruna, Sweden. Today, Vivek will tell us about his work on combined radar lidar observations. Vivek has received a very large number of awards. For instance, he's an AMS Fellow, and in 2018, he was awarded the Christian Huygens Medal of the European Geosciences Union. Today, we are using Slido to pose questions which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Please do not be alarmed if you cannot see your question, because we are collecting all the questions and then they will be revealed during the question and answer session at the end of the talk, at the end of the seminar. Dr. Vivek, we welcome you, and the virtual stage is yours.
Okay, thanks, Jan, for a kind introduction. Can you hear me okay?
Yes.
Thank you, Jan. For several years, I worked on polarimetric radar, looking at raindrops and ice particles. There are basically a much bigger size particle, about millimeter size, non-spherical in shape. I was using a polarimetric observations to come up with the scientific products, microphysical products like rain rates, type of the particles, liquid versus ice, and many types of retrieval techniques using electromagnetic scattering, understanding the microphysics. About 5 years ago, I was asked to lead cloud radar and lidar. These particles are much smaller, at micron size, 100 micron. They're almost spherical in shape, the liquid droplets. Then I got to go back and read literature. How do we use this information in our spherical drops using a cloud radar, cloud lidar, which are kind of new to me. I did a literature survey. With about 30 years of lot of work has gone before me. So I was wondering how I should improve the existing technique for estimating microphysical products. Basically, liquid water content, droplet size. There's so many other techniques exist in the literature. I like to improve on what I thought I could do with the electromagnetic scattering models and understand microphysics. That motivated to this presentation, or basically this work. Today, my talk consists of 4 major sections. The first part, I will go through a background about Stratocumulus cloud and the current status of the technique for retrieving liquid water content and droplet size. The second part would cover EM scattering, because I need to develop a end-to-end model. I can understand instrumentation response for a known Stratocumulus cloud structure. Use that model, develop retrieval technique. The third part will consist of retrieval technique, how I developed it. Then the last In the fourth part, we'll show application of the technique for the field measurements. With that, thanks to the NCAR HSRL team making this presentation possible, let's begin the presentation with PowerPoint slides. Let's see, click on the slide here. Okay, Stratocumulus cloud. The clouds are 100 to 500 meter thickness. When they are tightly coupled to the boundary layer, you see a very uniform cloud structure with the scales of turbulent eddies. When they're not tightly coupled, you see a patchy cloud like that. These clouds are very shallow, a lot of cloud drops, occasionally contain drizzle drops. It doesn't rain much. At the maximum, we drizzle. That's all you get out of that. Many times, even that could evaporate like a virga. Since ground-based measurements are not that useful or not possible, you need to airborne measurements to understand this kind of microphysical structure for this cloud. These are the type of cloud I'm going to be studying in this presentation and basically do my research. Stratocumulus cloud, it's very prevalent. It's about 23% of the ocean, more prevalent cloud, or land 12%. They are quite important for Earth radiation budget. And we need to understand, to do that, liquid water content droplet size, the key for studying radiative transfer effects. The cloud depth are about 100 to 500 meter. They're not that thick, but even about 100 meter, you might see some drizzle in those clouds. And so that's where the important, because even one drizzle makes a big difference remote sensing of DBZ measurements. These are the main issues with Stratocumulus cloud. Look at the instrumentation, what I used. I used two types of instruments, remote instruments. One is a hypercloud radar that's mounted on the wing of the airplane. Below the wing of the airplane, there's a part below that. It's about 13 feet part, 20-inch diameter, the part, within which we have a cloud radar. It's a 3.2 millimeter, basically, about 94 gigahertz. Very sensitive radar that was built by UIL engineers. Then other instrument, it's a green light, a LiDAR, micro pulse LiDAR, a state-of-the-art LiDAR built by Ed Alaranta in Wisconsin. We acquired that instrument. Both these instruments fly on the G5, Gulfstream 5. These two instruments, remote sensing measurements, I used in this discussion or in this research. Then Jan Jensen provided cloud probe, visit probe data from workers. And these are the in situ observations. NCAR cloud radar specifications. It's a 3 millimeter wavelength. Every 10th of a second, you get observations of a DBZ measurements. About 37 meters is the resolution along the range. It's a very good state-of-the-art radar, highly sensitive. We could measure DBZ measurements within a dB, wind measurement that 0.2 meters per second. The LiDAR is a green visible wavelength, 532 nanometer or 0.5 micron. The dwell time is about half a second because it's a micro pulse LiDAR, collect lots of samples, come up with the backscatter measurement. It's a 50 nanosecond pulse width, about 7.5 meter, the resolution along the radius. The more information about the LiDAR could be found in the following papers. One of 2015 Geoscientific Instrumentation, as Ed Alaranta, 2005, in a book he published a description about high spectral resolution LiDAR. In terms of challenge, what is the challenge we face in estimating liquid water content? This curve shows on the y-axis radar DBZ values, x-axis logarithm of liquid water content. The red particles or red color shows the drizzle. The blue dot shows, or black dots in this case, shows cloud droplets. Then blue is cloud and drizzle mixed together like that. Now, If you know if it is drizzle or a cloud droplets, for a given dBz, you might be able to estimate reasonably liquid water content. But in practice, we don't know that, what the cloud consists of, the drizzle or cloud, mix of cloud or drizzle. For example, as I wrote in the slide, 1,000,000 10 micrometer droplets, dBz is same as 100 micrometer droplet because of d power 6 dBz. But liquid water content is much different. For drizzle drops, it is just 1,000th of the cloud droplets for the same kind of concept what I described. Hence, for a given dBz, we need to know, are we looking at a drizzle or a cloud droplets or mixture of cloud and drop? Hence, once you know the droplet size, then we can do a very good job. That's the important thing to understand. Now, what is the current status of this retrieval technique? This is from Kane et al., 2008. They have a lot of power law relations. The top table shows Z, liquid water content relationship, the A and the B. Depending upon a cloud without a drizzle, you got a relation for A. For dBz values between -5, -17 dBz, that's about cloud with a light drizzle, have different relations. Like that, we have various relations exist by various researchers in the community. Then, estimate the droplet size, in this case, the effective radius, the function of dBz is valid only for when dBz is less than -17 dBz. That's only for cloud droplets. And very limitations with all these equations, what we find in the literature. Now, there are techniques which uses, in addition to dBz, they could use a two wavelength radars. Two wavelength radars like either W band or a Ka band, 95 or 35, or X band or Ka band, like that. They can do that. But we need two radars. Then it becomes kind of expensive, more complicated, matching the beam, matching the time and the space. And could be done, but it's more complicated. Also, people used radiometers, which measure the total liquid water path. Then they could come up with a dBz, some kind of boundary with the liquid water path with the radiometers. They can come up with the profile liquid water content. Again, we need to know the Z LWC relation, where it's a liquid water, consists of cloud droplets, drizzle droplets. Without that, again, that technique is also not that easy to implement. How about radar and Doppler technique, radar and lidar technique in this case? In case of Doppler, they could use spectrum width, skewness, kurtosis, all those things. This all done vertical pointing mode instead of scanning mode. And for that, we need to know ambient wind has to be known. Many times ambient wind is not that well known. And even in Doppler spectrum, it's not that easy to do it. The radar, lidar backscatter, most of the technique, they assume a droplet size distribution, is a gamma distribution or log normal or exponential. With that, they could come up with some retrieval technique. But it's an approximations. There's all limitations in the current technique, retrieving liquid water content droplet size. In summary, current literature, if you look at it, it assumes a mathematical form or droplet spectra, the gamma or exponential, like that. With that, they build the models. Then artificially, they have to partition the droplets in the cloud. It's 50 micron or greater than 50 micron based on dBz measurement, which is not that easy to do in practice. Then also, those retrieval technique valid only for a restricted range of radar measurements. And my objective was, could we at least improve the technique? Could we do better than this? So that we don't assume a droplet size distribution, or you don't have a priori as to know with a cloud droplet, drizzle droplet, like that. It's also valid for a far wider range of observations. Then this is my first part of the talk. The second part describes a simulation technique. Now, I need to develop the second part, describes an EM scattering model so that I can simulate observations of radar and lidar for various droplet size distributions, which is present in the Stratocumulus cloud. This is the single droplet size on the x-axis, the micrometer. From 1 micron goes up to about thousands of micron here in this case. The blue curve shows the backscatter. You see a Rayleigh scattering. About 300 micron, above that becomes a Mie scattering. Then you see oscillations, more optical scattering like that. The red curve shows the extinction or absorption, which increases with the size, then saturates to 2. These are normalized cross sections, what I show here. The blue is the ratio between extinction to backscatter. That means extinction or absorption is quite large in the small particles, then scattering increases like that. Then this is for 94 gigahertz for a W band, just a mono dispersion for individual particles. Similarly, I have to do that for LiDAR measurements. This is for a green light. What I show here is a blue curve shows the backscatter, the LiDAR, between 100th of a micron goes up to 600, 800 microns in this case. See the function of the size in x-axis. Initially, we see a Rayleigh scattering, quite small, like aerosols. Then as soon as the cloud droplet sets in, there are a lot of Mie scattering. Then it becomes even wild. The backscatter changes by a lot of values, like it's more than about 20 or 30 dB change for a fraction of size. This is basically a problem in a computing backscatter. You got to average, ensemble average, then we can reduce that fluctuation, the backscatter. That is shown in the last part of the panel here on the right side, the average backscatter, which is reduced all those oscillations. This took a lot of effort to make transfer from individual scattering to a lot of ensemble averaging, produce this plot, backscatter. The forward scatter is much easier to do. That's not that difficult to do it. Basically, it increases the size, that's it too. And with this kind of individual backscatter, then we could develop a complete instrumentation. This is collected by Jon Jensen, who gave introduction to this talk. In 2008, in workers in Southeastern Pacific, they collected lots of DST measurements using cloud liquid probe. This is a simulation here. For a radar, the y-axis shows attenuation in dB per kilometer. X-axis is dBz. The red dots corresponds to basically all basically in terms of cloud droplets, small dBz values, less than minus 20 dBz. But attenuation is quite large. The blue curve shows 18 times Z power like that. The green dots corresponds to drizzle droplets. The dBz is much larger, more than 0 dBz, you also given 20 dBz. Attenuation varies only between 1 to 4 dB, but the dBz varies by more than 40 dB, 40 dB of the dynamic range. Hence, big change in dBz values, but attenuation changes only up to 4 to 5 dB. This is a simulation shows for cloud droplet drizzle droplets. Now, for extinction, for in terms of LiDAR, shows the x-axis, the backscatter, y-axis extinction. This linear curve is very well known for cloud droplets or liquid droplets. The slope is 20. The extinction is 20 times the backscatter measurement. These are the validation I got to do before proceeding for detailed instrumentation response, because I need to have a kind of benchmarking so that I know what I'm trying to establish should match with existing results in the literature. This is the simulation of 83 ascents are descents of the profiles from C-130 profiles of Stratocumulus cloud. The top panel shows dBz measurements. The dBz measurements are shown between -30 or -40 dBz up to about 20 dBz or so in this case. You could see as the height increases, as you go up, values decreases. That's because it's a cloud droplets. Smaller the droplet size, smaller the dBz. On the bottom of the cloud, you see red like that. That's all drizzle like that. And that's much larger. This tendency is correct for a drizzle droplets. What I did, basically, it's a smaller dBz on the cloud top, larger dBz in the lower part of the cloud, or below the cloud base. The bottom panel shows the LiDAR backscatter, the beta, meter, and stadium units. It's the opposite trend. Most of them shows large values of beta on the top of the cloud because we got seeing a lot of cloud droplets for LiDAR wavelength, 0.5 micron. There's a lot of backscatter. That causes a lot more backscatter compared to lower part of the cloud where the drizzle droplets exist. And the trend is very consistent where we see large cloud droplet in the bottom, small cloud in the top, which causes W band dBz being higher in the bottom part, but LiDAR backscatter much larger, close to a cloud base or in the clouds. These are very consistent with what you expect to see. This gives me confidence about 83 profiles were able to simulate these backscatter measurements for radar and LiDAR. Here is the liquid water content on the x-axis, the gram per meter cube. Cloud droplets are shown in the red dots, green dots are drizzle droplets. dBz is larger. Liquid water content, basically, it's vary between hundredth of a gram per meter cube up to gram per meter cube, depending upon dBz values. But if you know cloud and drizzle droplets, then you can do that. That means we need to estimate the size very precisely. We can't be just having some average size. That's not going to work. How I did that, this is the key. This part basically onwards describes the retrieval technique. Here, the y-axis is the radar, LiDAR estimated size in micron. The x-axis, the radar backscatter ratio to LiDAR backscatter. That's in dB scale. This curve is basically no dispersion. How I define d6 by d squared for 93 bins, 30 bins of cloud droplet, 60 bins of drizzle droplets, ratioed up 1/4. That I called radar LiDAR estimated size. This size, there's no dispersion because how I defined it, that's why it is. Hence, I could uniquely estimate a droplet size. What is it? Without much of a dispersion, much of uncertainty, using radar LiDAR measurement. Once I do that, then for me, it's the technique is much easier to estimate liquid water content. That is a key. Now, I compare in the community, we use many other sizes, like a D effective, the bottom here and the bottom left. I compare the D effective size with the radar LiDAR estimates, is what I described in this talk. Then on the bottom right shows MED, medium volume diameter, shown on the y-axis, and again RLED. And this could be related if you assume a droplet size distribution. Thus, the RLED, what I described in this talk, related to D effective or MED, those MED and D effective are very good for in situ measurements and analysis. But remote observations, what I described here, using radar LiDAR backscatter, describing RLED is perfectly makes usefulness. That way, it's much easier to use without worrying about assuming a DSP equation in this case. With that, I show here what I computed in the case of liquid water content, and also RLAD, in this case, droplet size. Now, this is for 83 events, profiles done in vocals. Height is shown on the y-axis, up to 2 kilometers or so. And this is Stratocumulus clouds are shallow cloud, as I described earlier. Liquid water contents are large. The top of the cloud, you could see they're much larger, like that, as expected. Again, droplet size, they're much lower. RLAD, smaller size. The drizzle drops are much larger, droplet size. And these are the simulated for all those 4,650 droplet spectra arranged in profiles of descending, ascending profiles as C130 collected data sets that were shown. And these are the data sets I used to develop a simulation technique and validate. Since I know in an RC, observation simulation experiment, what's input, what's output, I could validate whether my technique, does it work in a very clear condition where no observation error like that. Now, this shows why I'm using radar and lidar measurements. In this case, I got these two measurements. They should be independent. If a dependent is not much usefulness, y-axis shows the backscatter from lidar, x-axis the DBZ measurement. There's no correlation. As expected, there are two independent measurements. That way, I could able to estimate microphysics using two independent measurements, not only DBZ, using lidar also. Here it shows same as, and our two curves are here on the top left is reflectivity shown on the y-axis, LWC. In the bigger curve, I have a size in micrometer and LWC. As you notice here, the RLED, the size, bigger the size, bigger the DBZ, as expected. LW for same LWC like that. Hence, I have two measurements now using two measurements, radar and lidar, as reflectivity and also ratio between radar and lidar, like a dual wavelength, like a radar and lidar. Hence, I have two independent measurements. That way, I could develop my technique. In summary, the size are estimated using radar measurements, which shown in the basically in the x-axis. Y-axis is the size. I could estimate size ratio between the z and the beta. 9.12 times z over beta, the 0.25 gives me the size between 25 micron or even 15 micron all the way up to 180 microns in this case. That means covers cloud droplets all the way up to even drizzle droplets like that. You could do that. Once I do that, then take a DBZ values, normalize that with a droplet size, then Z naught, that is what I plotted in the x-axis here, radar reflectivity normalized by the size. The x-axis are shown normalized reflectivity, y-axis liquid water content. Liquid water content shown as a linear relation as a function of normalized DBZ values. This is the summary of retrieval technique based using all the droplet spectra what I got from vocals observations, which is Southeastern Pacific, or the basically the marine boundary clouds, I guess. That's what I used it. To test my technique, I picked many spectra. Here it picked up event 1, the black curve, shows the narrow distributions. The magenta curve, the broad distributions, shown as a droplet spectra in this case. Like that, I picked up randomly number of DSD spectra, where it might be a cloud-based ascending descending spectra, basically. These are composed of each of those and computed DBZ values and lidar backscatter values. The top panel shows the height was a DBZ for 4 different profiles of Stratocumulus cloud. You can see the DBZ values for the blue curve is much lower, the cloud droplets. The The intermediate plots, two of them shows dBz between -10 to 0 dBz. The magenta one shows much larger dBz, 0 to 10 dBz or so. And it's picked up various types of cloud profiles. On the top right shows LiDAR backscatter for same profiles of liquid water contents in this case. Interestingly enough, LiDAR backscatter increases with the height because the cloud droplets are increasing with the height in stratocumulus cloud. That's why it's higher. But the radar measurements, as you see in the top left, decreases with the height because the droplets decreases compared to bottom below the cloud base. Very consistent, the four profiles they picked up. Then the bottom left shows radar-lidar ratios with the height. You can see that basically they're all vary between 10 to 50 dBz. That's what I used to retrieve the droplet size. The bottom right corner, last plot, shows LiDAR ratio. For a blue curve, you could see about 19 or 20 in this case. This is very well known. For the cloud droplets, numbers about close to 19 or 20 like that for a LiDAR ratio, which is extinction to backscatter ratio. That's what it is. But if it is not cloud droplet, that value could change depending upon droplet size and mainly in this case droplet size. Okay, this is the simulated observations where I computed using the radar lidar simulated values, size, and the 6 curves on the top all correspond to size. The top left shows what I retrieved. The x-axis is the size, y-axis is the height. Microns, the blue curve shows very small droplets in this case, 30 microns or so. Then two interior curves shows 60 to 90 micron droplet sizes as a function of height. The magenta shows much larger, 120 to 150 micron. And so depending upon this, as you recall, this corresponds to broad droplet spectra. This is a narrow droplet spectra, blue curve, the intermediate. Now, since I have an in situ measurement, I validated what I retrieved and what's the true measurement. You could see that within about plus minus 5 micron, I could do that. Most of the particles I can retrieve even less than 1 micron. And very precisely, I could retrieve particle size in a simulated situation like that. There were 4 events, for all of them less than 1 micron. One of them goes up to 5 micron for the broad spectra, the error, in situ minus retrieve. The percentage-wise, that means within a 5% accuracy, the absence of any measurement error, I could retrieve the particle size using a radar-lidar measurements. I got really enthusiastic once I saw these results, able to come up with a very accurate way of estimating droplet size. The bottom 3 shows liquid water content estimate. The first one, liquid water content, for the blue curve, less than 0.2 gram per meter cube. Other values based 0.1 to 0.5. The bottom middle panel shows the difference between in situ and the true value. That's the true value between the retrieved values, I'm sorry. That shows the values, the error is about less than plus minus 0.2 gram per meter cube, what I estimated in this case. Now, in the percentage wise large because my liquid water content is much smaller. This is only for 4 profiles, what I showed here. If you look at for all the 4,650 DSDs and the profiles of 83 profiles, the accuracy on estimating droplet size, RMS error, is less than 2 or 3 micron droplet size. For liquid water content, is less than 0.02 gram per meter cube on the overall, if you look at it. That's the RMS error, is less than 0.02 gram per meter cube liquid water content estimate. I got all this retrieval technique developed, then I need to apply this for field measurements. this is the last part of the presentation where I used field measurements. That's done in 2015. The technique was developed in Workers in 2008. That's the Southeast Pacific. Now, these measurements are taken Northeastern Pacific over the ocean, again, marine shadow cloud, shadow schema cloud, in July to August. Here, we had number of remote sensing measurements. The cloud radar, hypercloud radar, the footprint for that varies depending upon how far the cloud from the G5 or from the Gulf Stream. 4 to 35 meter footprint could vary. LiDAR footprint is 40 centimeter, the footprint for LiDAR. Then the radiometer we had, that's a G-band radiometer, 183 gigahertz. The footprint varies from 10 to 90 meter. Along the flight track footprint is 70 meter, basically, every second, basically. HSR footprint is about displaced from HCR, how they mounted it, 142 kilometer range. Anyway, that's not that important in this case. If you look at it, you have a cloud radar, it's a meter resolution or tens of meter. LiDAR is about 40 centimeter, less than a meter resolution, in centimeter resolution. Radiometer is about close to 50 meter resolution. Each has a different footprint. They're all on moving platform. Then I got to use these measurements to validate. Otherwise, all the technique what I developed using simulations doesn't make any sense unless I validate this with some kind of field measurements. This is a challenging part. It took a lot of time to pick a right data set where I could look at radar measurements. They are vary between, if you look at the top panel, it shows 5 minutes of flight path. This is about 42 kilometer distance, 5 minutes. DBZ values, you can look at basically optically thin cloud, then optically thick cloud, then drizzle coming off the cloud base. You can see the variety of cloud types in this 40 kilometer swath. I picked this time frame where I could apply my technique and see whether I can able to retrieve cloud droplet, drizzle droplet sizes, and also liquid water content. But I had only a single airplane. I don't have a secondary airplane where I could compare concurrently what I retrieve, how to validate. Hence, I got to rely on the radiometer for that case. Before we go there, the middle part, sorry, let's go back to it. The middle panel shows the LiDAR measurements. You can see very clearly the cloud base, the lot of LiDAR backscatter. Below that is basically a drizzle coming out of the cloud. The radar tail, you can see that. Again, the same thing with LiDAR. LiDAR is very high in the cloud base, but above the cloud base. The bottommost panel shows DBZ corrected for attenuation for a radar. But the LiDAR is already corrected for the backscatter because LiDAR HSRL is the state-of-the-art LiDAR where it makes use of the backscatter from free clear air and also from the cloud that they can able to estimate attenuation and able to correct for that. Since I got these remote observations, for that, I applied the technique what I described using radar LiDAR ratio and DBZ values, estimate liquid water content. Here is the retrieved quantities. The top panel shows the droplet size. Droplet size in the cloud base is a blue color, deep blue color, about less than 20 to 50 micron, even less than 30 micron in this case. Most of the droplets are less than 20 micron. The drizzle is close to about 0.4 or 0.3 millimeter. Big drops, drizzle droplets exist in there. You will retrieve that. Same thing in here, drizzle, and you can see a lot of cloud droplets. The bottom panel shows liquid water content. Liquid water content is large, 0.2 to 0.3 gram per meter cube in the cloud, as expected. The drizzle is less than a tenth of a gram per meter cube. You can look at it. And it's very consistent logically how the cloud base, you got a lot of below the cloud base, liquid water content is much lower. In the cloud base or above the cloud base, it got much larger. So now we got to validate this. Since I don't have in situ measurements, I use the radiometer. So the 40 kilometer swab. This is the last but one slide where I did sum up. Let's go back to the previous slide. What I did was the liquid water content in the bottom panel. I summed up all the way up to the whatever I could measure it. It's a liquid water path. I summed it up. That is compared with the radiometer measurements, W-band radiometer measurements, G-band radiometer measurements. Here, the red curve shows radiometer, same, a 5 minutes time frame. The blue curve from the radar and lidar, what I summed up liquid water path, shows very clearly the structure well matched, given the amount in a good range. Even if you recall, the radar footprint is much different, radar footprint. Radiometer footprint much different. They're all moving platform. I got to average. Each one is taking a different time scale. Radar takes up 1/10 of a second. Radar takes up half a second. Radiometer takes about 6.5 seconds. So I got to average along the flight track, but I don't have much control across the flight track. At least I did good averaging along the flight track. Then compare this measurement. And so the RMS error between radar and lidar is 1/10 of a millimeter for this case. And this validated the technique what I developed using radar lidar for estimating liquid water content droplet size. Of course, droplet size is not validated, but logically it fits. Smaller cloud droplets, the cloud base, larger drizzle droplets below the cloud base. Now I come to the last slide. In summary, when we have a state-of-the-art radar, W-band radar built by EOL engineers, we acquired a state-of-the-art HSRL from Ed Alaranta from Wisconsin. They're the best instruments what we have in the community now. We come up with a technique which is much better than what existed currently, that applies to wide range of DBC values for all values of LiDAR backscatter. This technique is developed using droplet spectra collected by C-130, our own airplane, in vocals. Those things are basically used. That technique is so robust, we could use this in Northeastern Pacific to validate this. And this solid physics in this one, what we come up with retrieval technique. The root mean square errors are very small in terms of droplet size, a 1/10 of a micron, or even 100th of a gram per meter cube, we could estimate droplet liquid water content. If we add instrumentation error in this case, then it will increase basically about 7% error in estimating droplet size, about 15% error liquid water content. Compared to current technique, liquid water content estimates about 50 to 60% using those relations what exists in literature. Hence, our RMS error is much lower, less than 15 or 20% for liquid water content estimate. And the technique is solid, independent of a geography or where you do this. As long as you got a radar measurements, you can apply this technique, then come up with a droplet size and liquid water content. Mainly why it's possible, because we use the two measurements, radar and lidar, estimate droplet size. That in turn helped to retrieve liquid water content in a broad DBZ values and lidar observations. I would stop here. Thanks for listening. I'm happy to take any questions you might have. Thank you.
Well, thank you very much, Vivek, for such an interesting talk, and how wonderful to see the application of data and so many of EOL's data sources, instruments in such a comprehensive analysis. So whilst we wait for the Slido questions, I just have one here right now. On your plot where you showed a comparison between the radar LiDAR and the radiometer liquid water pass, the radiometer liquid water pass never went to 0. So was that because of a calibration error, do you think, or was it because it has a much wider viewing angle than the radar LiDAR?
Yeah, my thinking is the radiometer covers much wider, or not wider, in fact deeper in the cloud. It picks up everything, what is out there. The radar technique, I did only both measurement coexisted. And there is a spatial difference between what radiometer observed, what I computed, because my technique doesn't work when there's no LiDAR measurement, because it depends upon both this measurement coexist. Many times, what happens is above the cloud base, in this case, G5 was flying 300 meters above the ocean surface. When you look up, I got all the excellent measurements up the cloud base, but above the cloud base, there is some cloud still exists, which is not seen by the LiDAR, and so I couldn't do that. And that could be the reason why there is a residual thing radiometer shows, but we're not picking up that. And so you are correct, yeah, it's a radiometer picks up everything. We're able to pick up only, quantify only where both observations coexisted.
Yep, thank you.
Yeah.
So can we have the first Slido question? And I don't see any right now.
Okay.
So, let me just ask. So actually, please come with more questions and so on. But I do have another question for you, Vivek.
Yeah.
And that is, can you extend your method to ice clouds?
Okay. Very good question. That's, in fact, we are going to I'm getting a literature review on that one. We are going to get started on that. The ice particles, simulation of LiDAR back ice scattering has to be done as the ice exists in various habits. Then it's going to be much more challenging because of now various particle shapes and the density. It's going to be a lot more challenge. But there are some work has been done in this case, but it's just using a DBZ only. And coming up with using radar and LiDAR, it's going to take a lot more efforts to do that. I'm going to do some kind of approximation for ice particles. I may have to come back to Jan at some point, ask you how to do that, or just to do that work. And simplified, because ice is kind of complicated scattering. And I'm planning to do that. The W band doesn't attenuate to the ice that much, snow and ice that much, but the LiDAR will do it differently. And so I got to do those computations and do that. And so I'm planning to do that hopefully in the coming months. Yep.
Yep. Okay, thank you. And to all of you out there, you can ask questions by scrolling down to the bottom of the page, and then please add in also your name when you ask a question. So we have a question here from Ulrike Romatschke. Did you only validate the one case from CSET that you showed with radiometer data, or more cases?
Yeah, I looked at in CSET only so far, because CSET was a warm cloud, not much ice contamination. I looked at about 3 to 4 other cases also. I haven't shown the results yet. In fact, when I started radiometer comparison, I was warned by the PIs. Radiometer calibration was questionable, and maybe you have to be careful. Then I talked to Andy Pasmani, who was the instrumentation, who developed the instrument. He did the retrieval. He gave me a confidence. Yeah, you can look at it. But I got a mixed messages from the PI, from the instrumentation developer. But somehow I took a bold step to look at the radiometer data. Hence, radiometer data, what existed, only limited cases. Also, the radiometer data has to be upward looking, because it's always upward looking. Hence, only the airplane or G5 flies, below the cloud base, then we have a good path measurement. And I got affected very carefully when the radiometer is looking up, so that covering the whole cloud. That way I can get good observations. And so those observations are there. I looked at 3-4 cases. Yes, there are other cases where we could do this study. And this study, once you do that, currently Ricky is looking at it, the down-looking mode. And so where we could use this up-looking mode to compare with at least some kind of base to compare with that. And so we have competing techniques or also alternative techniques to come to our Cont estimate. They are quite helpful as we move along. But this is a methodology where we had a perfect data set where we got observations all the way from cloud, where the drizzle, all in the cloud base, then also with no ice phase. It's ideally suited to validate what I developed in this case. It's very rare to get those kind of measurements to do the validation. Then we can go to complex cases and challenge ourselves, see how good we can do it. Thanks, Vivek.
Thank you, yes. And do we have another question? The next one here is also from Ulrike Ramatke. How much suitable data do you expect given the fact that the LiDAR generally doesn't penetrate deep into clouds?
Yeah. I talked to DOE scientists about that because I don't have much experience looking at lots of data set. One of my co-authors in this case from DOE, two of them, they said there are optically thin clouds, so much exists in the atmosphere. And so this technique, according to them, is quite helpful because a lot of these clouds are optically thin. For those situations or those scenarios, this technique is helpful. Since it doesn't penetrate cloud base, yes, it's limited. Yes, there are, in the cloud base is present, a lot of cloud droplets exist, then yes, technique is limited in that case. But till we get cloud base, then in a up-looking mode for a ground-based observations, or up-looking mode when the airplane flies close to the surface, then we can do this. Otherwise, we are limited. And so that's the impetus currently within UIL. How do we come up? How do we, compensate for this? Could we do radar only or some reference to sea surface technique? Could we do that? Each of them will have its limitations because sea surface scatter, it's highly fluctuating due to ocean waves and various parameters. How good you can estimate the attenuation backscatter, against the questionable, but I mean, there's a CloudSat, they do that. And there are community, people do that. Hence, we are going to be attempting in the direction, see how we could come up with a technique where when the clouds doesn't penetrate into, LiDAR doesn't have the good measurements, how we could come up with droplet size equivalent content. That will be a technique. We'll work on that within RSF or UIL in the coming months. And so this is an interesting area to look at it. For me, it's quite new, and so I learned a lot working with radar LiDAR observations, the simulations. I have this end-to-end model where anyone interested, they could look at it and look at it a bit more in deeper in what they did.
Okay, thank you. Any more questions here? Otherwise, I have a third question, which is, if you remember from CSET, with the flights between Sacramento and Hawaii, one of the things that Rob Wood was very much focused on was the so-called veil clouds, like very, very thin layers caught under small inversions. There was a lot of argument if this was transport from like anvils from some of the trade wind cumulus clouds, or if it was generated in situ and so on. And even if you don't have the radiometer data for that, have you tried to see if these veil clouds were kind of outliers, or were they part of the usual thing that you saw as part of the whole CSET data set?
Aha. I haven't looked for that. Maybe if you come to the time period when that existed from the PIs, I'm happy to look at it, see whether radar saw that. If any cloud drops present, radar would have seen that, because radar doesn't see the any aerosol, but if you chase the LiDAR should have seen for sure. That'd be interesting to look at it. If there are veil cloud like that, we could take a look at it. And this type of clouds are, if they have both coincident LiDAR observations, and so we could characterize them in terms of, microphysics. It's possible.
Yeah, and they were optically thin. They, from memory, they had sort of between 1 to 5 cloud drops per cc, and often they were surprisingly large drops in not tiny drops and so on. And the aircraft did do some profiling through some of it. So by looking at Rob Wood's paper on those veil clouds, I think it should be possible to look at it from a remote sensing and in situ comparison situation. And he found that they were remarkably common over the subtropical to tropical oceans.
I see. That's good to know. Is there a Rob Wood's paper? He published it, or could you send me a link on that, Jan?
I will have to search around, but yes, we can.
Okay, appreciate that. That takes literary effort. Yeah, thank you very much. I'm happy to take a look at it and see whether we can do that. In fact, all this product, Rike, currently implemented for operational. Actually, she can do basically in a limited time, what she has implemented. And we could look at some of these features once we know where it exists and see whether, how useful the technique what I presented today to characterize some of these cloud types. And from my part, I'm just being an engineer here, come up with a technique which I thought it's much better than currently what existed in the literature, and validated that. The JTech paper, what we published together, it's really a eye-opener for me. In fact, we got such a good reviews, and people reviewed it. They said it's one of the improved technique compared to what currently exists. And so I'm very optimistic this technique could be extended. Look at some of the big drops, and where we have a good big drop. Sure, SCR would have picked it up, and the LiDAR. I'm sure there are, good observations. We can do that. But our measurements are very good. Our calibration is very good. Data quality is excellent. I doubt anyone could, even come close to what we do in the community, to my knowledge, because our LiDAR is highly calibrated. The radar is a very nice calibration with the various ways how they do that. And so I have a good confidence in the observations. So.
Okay. That is great. And do we have any final questions? I don't see any. So with that, let us end this, and thank you all very much. Thank you, Vivek, very much for such an interesting talk, and thanks for educating us. That's great.
Oh, Jan, thank you for now providing the data sets. Now that's the key.
You're welcome. Thank you very much.
Okay, appreciate that.
Bye.
Bye.